Hi there, this is the AMD AI Engine project, making AIE development easier. We're a two-person team. My partner Graham here is on the left. Myself, Francisco, am here on the right. To give some personal background, Graham and I are part of the Supercomputing Club, and we were looking to do some FPGA development. That's when we came across AMD's open hardware competition, and we started looking more into Xilinx FPGAs. That brought us to the kind of obscure and underutilized AI engine. Now this technology is included in Versal FPGAs, and nowadays it's also included in AMD's Ryzen AI series. This architecture is very special. It has many types of parallelism: data parallelism, memory, spatial, instructional parallelism. The architecture is very unique. There's a lot you can do with it. However, there's just not one single way to program them, and there's a lot of lacking examples. And I think because of that, this has led to slow adoption, some confusion, and not a lot of programming for them. So, to top it off, some of the examples or some of the documents and diagrams for marketing are just incorrect. Seeing this demand to create more code for them and seeing that it's just kind of a space that we can fill, that brought us to our project. Our goal, if we had to bring it to one word, it would be documentation. The favorite part of a programmer's process. So in our project, you'll find a read the docs as well as some examples, as well as just explaining the architecture, the features, the development space, and overall just tools that we wish we had. Okay.
All right, so we are doing every programmer's favorite thing, the most exciting thing. We are writing documentation. Now, we actually start out with the more general architectural perspective. We compare the AI engine versus GPUs and other accelerators. This is particularly useful for those programmers that come from a GPU programming background. AI engines are essentially grids of processors that run kernel programs, somewhat similar to GPUs. One thing two major challenges that we wish to address that we noticed when we were writing our own examples is that optimizing data movement on AI engine is hard, and limited local memory per tile is very small, being only 32 kilobytes. So programmers need to overcome these challenges. Now we address these challenges through examples. Here we can see we implement a sequence of bypass kernels that don't compute anything, but they do move data around the grid in an efficient way. We use constraints to map kernels to specific places on the grid so that they can do direct read and write access between their neighbors. It can result in fairly complicated data access patterns like this, where the data is snaking up through the AIE array, like so. We also have basic vector addition on a single tile, and we use it to talk about buffers versus streams. As you might think, streams offered lower latency, but also lower overall throughput because buffers allow you to more efficiently utilize the SIMD nature of the processors. We also have single tile matrix multiplication, which we extrapolate onto 16 tiles and do 16 by 16 matrix multiplication. There's a problem with this code though, which is that it duplicates the input matrices in all 16 of the tile's local memory, which is highly inefficient and not scalable at all. To get around this, we use an addition tree implementation. This is also very useful for skinny A matrices. So if you're multiplying skinny matrices together, you might want to split up the first matrices by columns and accumulate partial results by summing them. And we do this using the addition tile. We also have miscellaneous programming examples like convolution. And we finish with multi-layer perceptron, the simple architecture, which classifies the MNIST dataset. This actually uses the matrix multiplication code from our multi-tile addition tree. Unfortunately, we've ran into some problems, for example, to do with converting different integer types between accumulators and vector registers. So we have not been able to get it fully working, but it's almost complete. The MLP, that is. Well, thank you. Thanks for watching.